Okay, mic's working, we're live, very good. Okay, so we're gonna continue where we left off in the last video because we are talking about Smagorinsky model. Just want to start in putting in the correct boundary conditions first. Because Smagorinsky model likes to operate on this nu t. Okay. Smagorinsky model likes to operate on this variable nu t rather than k, epsilon, nu, tilde, and omega. Actually, all of these you can kind of ignore. You only need nu t, p, and u for Smagorinsky model. You don't really need any other kind of boundary conditions there. So let's go to nu t, and we'll paste this right here. All right. And then I'll paste this at the bottom, and I'll paste this here. Okay, let's go here. All right. Oopsie, better undo that. And actually, you can just press U to undo. You don't have to always press a semicolon if you know what you're doing. That's for VI. Okay, let's delete some of these lines and delete this. Okay. Yeah, I think I deleted too many brackets. So that should work. Okay, CP 0.original nu t into 0 nu t. Okay, so let's go 0 and see the nu t there. It is exactly where we want it to be. All right, and then we can run PimpoFOAM here. Okay, so things should solve okay. All right, so looks like things are running pretty okay here. So I'll just not finish, but yes, these are how you're supposed to put your boundary conditions for the Smagorinsky model. Okay, k, epsilon, nu, tilde, and omega you can ignore. You just need nu t, the pressure field, and the velocity field. That's all you need for Smagorinsky in the PimpoFOAM. So actually Smagorinsky, as you can see, is pretty simple, straightforward. Now let's go and look at k equation. Right? We noticed that just now we had an error, so I'm going to repeat it so that you know what this error is. Okay, let's go PimpoFOAM, and then you will see some sort of an error. Unless I already fixed it. Yes, okay, I have not fixed it yet. So cannot be, say a form fatal error cannot be called for calculated FV patch field. FV is finite volume on patch blah 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 in the k boundary condition. So what's the problem here? We see that when we go to k, all of these are actually calculated. So that's not good. We are supposed to have accurate boundary conditions there. Okay, in here, nu t can be calculated. Okay, epsilon should be calculated. Nu, tilde, and omega should also be calculated, but k cannot be calculated. All right, so I show you those so you can see they are calculated. So we need to put in an appropriate k field, and where we can look again, it's how do we set for k equation this field? Well, let's see. We can do a wall function for the wall for sure. So let's take a look at k omega SST IDDES, or even better, we can start to look at what do you call that? We can look at the tutorial cases to see how they set their boundary conditions. So let's go to Foam Tutorials. Okay, and we go to incompressible. Let's look for k equations. All right. And you will see here, we just saw the decay iso turbulence last time. That's one of the places we use that. We also see it in the turbulence properties. So let's take a look at this case to see what's the case like, the case structure. So we only have nu T and P. Okay, looks like it's all cyclic. Okay, so it's not exactly a flow case. It is not exactly a flow case, and it seems to be missing an entry for K, the turbulent kinetic energy somehow. And let's see if the all run here has anything. Says create block mesh with this create box turb utility. Okay, so it creates a turbulent structure in a box. So this is not exactly a file that's very similar to us, right? Oh, look, here's where you have your kinetic energy table. Okay, this is energy as a function of the wave number. Okay, so it's not exactly a box that we want to deal with. So let's try grep kEqn. You'll find that the other case is the channel 395 Df-Sem. Okay, channel 395 Df-Sem. What's Df-Sem? Df-Sem is actually one of the ways, you know, at the inlet. Okay, it's actually one of the ways to artificially generate turbulence. So if you have a pipe flow, with this with some velocity, fluid or velocity going in, we don't really have turbulence here. Okay, you don't really have turbulence here because the velocity fields are not fluctuating with respect to time. And for large eddy simulations, you resolve part of your turbulence as viscosity, and you resolve part of it using a velocity field. That means you will actually see the velocity field fluctuate every now and then, as if it was real turbulence. So how do you actually have turbulence generated at this part? You will use this thing called the Df-Sem, Divergence-Free turbulence generator or something like that. I can't remember what it is, but okay, anyway, this is one of the boundary conditions, and you will see here there are 4 fields. One is K, one is nu T, one is P, and one is U. So for the K value, now this is actually a channel flow, so we will have fluid flowing. Okay, it's like a 2D flow in a channel, but yeah, it's like a 2D channel flow, but they use a 3D kind of model to simulate it. That's why you have these cyclic boundary conditions. I'll go more into cyclic boundary conditions much later on, don't worry about it. But the one I want to drive at is this boundary field. Okay, boundary field at the top and bottom wall. So looks like at the bottom wall and top wall, a wall function isn't actually used. What was used is this fixed value of 0. Okay, so what does that mean? That means that actually you just have 0 turbulence kinetic energy at the wall, which is exactly what we want. Alright, so of course you have to calculate your own turbulent kinetic energy somehow, and the way to do it for LES is not exactly the same way you'll do it for you won't do it the same way for how do you say? You won't do it the same way for a Reynolds average Navier-Stokes. So I mean, ideally you want to simulate 20% of the turbulence. You want to put it as some sort of you want to put 20% of the turbulence in the turbulent viscosity kind of a manner. So yeah, maybe one of the ways, easy ways, is to take the take the value you would normally use if you have a k epsilon model. You have a kinetic energy k there. You use that value and you divide by 5. You roughly more or less be in the ballpark of where your turbulent kinetic energy is. I mean, that's a easy estimate anyway. Okay, so let me put it into the comments here. I may or may not be right, but this is where you can start off. Inlet K, kinetic energy for KE, K for boundary condition can be 0.2 times of inlet K for rents. So what am I saying here? Okay, what's the rationale here? Okay, so remember in your Reynolds average Navier-Stokes, case, you would have some turbulent kinetic energy here, which you will use some sort of turbulence intensity I. Alright, you will use some sort of turbulence intensity I to calculate the K over here for rents. So I guess the simple way is to for LES K equation, you take whatever this value is and you times 0.2, because ideally speaking, you want your large eddy simulation to resolve 80% of the turbulence in terms of energy. The remaining 20% you want it to register under the modeled quantity, for example the K energy. So that's what I'm talking about here. Alright, so anyway, at the wall we should have a 0 okay, let's undo that. Alright, we have to do a fixed value of 0 at the wall. Okay, top patch, let's do 0 gradient because everything is kind of exiting. Okay, that should work for the time being. If there's any instabilities, we can of course change it around. But if you take a look at how this case is structured, okay, alright, this case is not structured in that manner. I mean, the inlet and the outlet will use a fixed value, so we'll just stick with that because that's actually pretty stable. 0 gradient may not work because when you have recirculation of flow, I mean in large eddy simulations, okay, in large eddy simulations you have a recirculation of flow. So what do I mean by that? Okay, let's delete this, clear the blackboard, and we'll start here again. You'll have this situation, and let's say this is the outlet. It's the outlet, and in the outlet patch you will have some, or maybe I use this, you will have some turbulence over here, and then you'll have some sort of a backflow. Okay, now when you have backflow like this, it can cause errors. Alright, it can cause errors. Okay, can cause numerical errors into the solver, so you may not want to use a 0 gradient boundary condition. What's better is to use this fixed value. Use a fixed value, and that should actually stabilize your whole simulation. Okay, of course you can actually use the turbulence intensity method. Alright, how do we do it? Yeah, we can of course use the turbulence intensity method. Alright, okay, pimple foam list scalar BCs. You can use this turbulence intensity kinetic energy inlet, then you kind of multiply your intensity by 0.2. I mean, that's one of the other ways of doing it if you want to achieve that 20% idea, because you have this from the RANS case. From RANS, you have your inlet turbulent kinetic energy calculated like that. For LES, you can do 0.2 times 3 over 2 I times U squared. Alright, so if you input in OpenFOAM, the only way you can put in variables is to define an I. So if you, let's say, have an actual turbulence intensity of 0.1 and you want to use this particular method, the turbulence intensity kinetic energy inlet, and you want to use that as your boundary condition, you should multiply it by this 0.2 or less. So 0.2 times 0.1 times 0.1, and that will be the I that you put in here. But that's if you want to use that method. Not necessary. I mean, the most stable, as you see in the tutorial file case, is to use what we have here. We just give a certain fixed value to this. Okay, but I mean, if you just talk about syntax, either is fine, but you need to know what you're doing in terms of how you calculate what kinetic energy to give it. Okay, you gotta be very sure of that. Okay, so that's more like under theory and all that, but so I won't cover too much on that. I'm just showing you how to write the boundary conditions and make sure the solver doesn't crash. Okay, so if I run pimple foam, it should be able to run nicely now for the next time steps. Okay, so again, it looks like there's still a problem, because I think I changed the files in the 0 original. Okay, so I need to copy cp 0.orig original /k into 0k. Then I run pimple foam. Okay, this time it shouldn't crash. I forgot to copy the files over just now, that's why. So see, now the simulation's working. So that's how you do your K equation, and that's how you do your Smagorinsky well. Of course, the last one I want to do is this whale, and okay, maybe I'll just show you all four, might as well. Pimple foam, LES, dynamic K equation. Alright, let me do this. Pimple okay, so I'm making a dynamic K equation case. Let's go to dynamic K equation. Alright, and we'll go to constant and we'll see the turbulence properties here. Instead of K equation, we'll do dynamic K equation, and the delta we will change accordingly. So this is just syntax for that. I'm not particularly too physically accurate about the way we are doing things, but I'm just showing you how to put in the syntax, and that's it. Okay, so for this dynamic K equation, the model inputs you need are the same as the K equation. Okay, let's see if there's anything else, but let's try and run PimpoFoam first, see if there are any errors. Okay, looks like I spelled dynamic K equation wrong. So I need to capitalize the K. Turbulence models, turbulence properties. Okay, let's run PimpoFoam again, and my time is almost up. Let's see how much time I have left. Yeah, it's about 20-ish minutes. Wow, this is actually taking all okay, so yeah, it basically yeah, it's doing its job. It's simulating, so doesn't look like too much of an issue over here. Okay, anyway, that's all I have for you. I basically showed you how to do Smagorinsky model, K-equation model, and dynamic K-equation model for syntax. So next thing I want to do is go into whale model, the more adapting local eddy viscosity model, and yeah, you'll proceed from there. Thanks for watching.